Part 2 of Unit 5 is the basics of the quantum mechanical model. Erwin Schrödinger developed a model that incorporated the wave and particle nature of matter. It was an equation that he came up with, and the square of that equation produced probability distributions to find the locations of electrons. This complicated equation was called the wave equation, and these probability distributions, they show the statistical likelihood of finding an electron at any one time. Now, we can never know both the speed and location of an electron at the same time. We either know one or the other. That's part of Heisenberg's uncertainty principle. But these show probabilities of locations of finding that electron. Where you see dense areas of dots, there's a high probability of finding an electron there. In areas out where there's fewer dots, that means there's a lower probability of finding electrons that far from the nucleus. Solving that wave equation gives a set of orbitals and their corresponding energies. Orbitals are specific electron density probability maps, so they're specific pictures like the ones we just looked at. Each orbital describes a specific distribution for that electron density, and an orbital is described by a set of 3 quantum numbers. Those 3 quantum numbers, one is the principal quantum number, the second is the angular momentum quantum number, and the third is the magnetic quantum number. The principal quantum number, it's got the abbreviation lowercase n, and that tells us the energy level of the orbital. It can be any number 1 or greater, and that's pretty simple. It's just the energy level. If you think back to the old Bohr diagrams of the circles around the nucleus, it's the principal energy level of that orbital. L is the angular momentum quantum number, and that tells us the shape of the orbital, and it can be any number from 0 to n minus 1. So if we're looking at the 4th principal energy level, where n equals 4, that means the angular momentum quantum number could be 0, 1, 2, or 3. It's always going to be 1 less than the principal quantum number. And m sub L is the magnetic quantum number. This tells the 3-dimensional orientation of the orbital, because atoms don't exist flat on paper or on a screen. They're 3D things. And the value of the magnetic quantum number can be any number from -1 to 1. So -1, 0, or 1. Orbitals on the same energy level, or orbitals that have the same value of n, they make what's called a shell, and different orbital types that exist within a shell are called subshells. I didn't include a page for n, the principal quantum number, just because it's easy. It's the energy level for that orbital, 1, 2, 3, 4, whatever. But looking at angular momentum quantum numbers, values for L are assigned letters, because that's easy, right? But it's based on early research into the shape of those orbitals, so you're going to need to remember this chart. If L has a value of 0, that shape designation is an S. 1 is a shape called P. If L is 2, it's got a shape designation of D. And if L is 3, it's got a shape designation of F. Now, the values of L do go higher than that, but I've never seen anything dealing with anything higher than shape designation F, so this is all we're going to look at too. Looking at s orbitals, they've got an L value of 0, and they have a spherical shape that increases in size with the energy level. There's only one s orbital per energy level, so for every principal energy level, for every n, there's only going to be one s orbital. And s orbitals are pretty easy to remember, because you can think s in sphere. That's not the root of how it got that designation S, but it's just a happy coincidence for us. S orbitals have a spherical shape. The 1s orbital on the first energy level is smaller than the 2s or 3s, so you can see that the size of this electron probability map is increasing with the energy level. p orbitals have an angular momentum value of 1. They got a dumbbell shaped orbitals that exist in 3 axes, and again the size increases with energy level. And there are going to be 3 of these p orbitals per energy level. So the 3 p orbitals are exhibited in these 3 pictures right here. There's one on the x, y, and z axis. And for a single atom, they all exist together. So if we combine them, this is what they would look like in a single atom. So remember, these blue areas are showing the probability of finding an electron in that p orbital. It's not as much of an area as the s orbitals are. For an angular momentum value of 2, we've got d orbitals. And the first 4 orbitals are shaped like clovers, and then the 5th one, it looks like this weird guy over here, a dumbbell and donut looking thing. There are 5 d orbitals per energy level, and again, these also increase, the size of these increase with the principal quantum number. So the higher the energy level, the larger the electron density map, the larger these orbitals are. These look really crazy when you combine them all onto the layout of one atom. And then for an angular momentum value of 3, we've got f orbitals, and I'm not even going to begin to try and describe these shapes, but this is supposedly what they look like. There are 7 f orbitals per energy level, and I don't have a picture of all of these combined onto one because it would just look like gibberish, but anyway, these are the 7 different shapes of the f orbitals. Okay, this table gives a nice summary of those quantum numbers: the principal quantum number, the angular momentum quantum number, and the magnetic quantum number through n equals 4, the 4th principal energy level. Compare these rules to what you wrote down earlier. Try to build a connection between the number of orbitals, the subshell designation, and the magnetic quantum number. Your question for this section: angular momentum numbers of -1, 0, and 1 indicate which letter of orbital?